In this lecture, we are going to discuss refinements of your path tracer, taking into account importance sampling and handling BRDFs. We will start by discussing cosine sampling. We've already talked about importance sampling in the context of Monte Carlo path tracing. In this assignment, you will implement importance sampling at each bounce. You will use a good PDF for sampling instead of the uniform probability distribution function. We will also discuss an extension to multiple importance sampling, which is a famous paper by Eric Weech and Leo Gibas in 1995. It allows one to combine multiple importance sampling methods such as sampling according to the lighting or according to the BRDF and the scene. It's widely regarded as a key development in physically based rendering and Monte Carlo path tracing. In fact, it is so important that very recently it was issued a Technical Academy Award, actually a Scientific and Engineering Academy Award to Eric Weech. And it remains a topic of active interest. In fact, there were several papers just the past year in 2019 at SIGGRAPH and SIGGRAPH Asia discussing new methods for importance sampling and multiple importance sampling. First, we'll talk about cosine importance sampling. We want to include the cosine term in the probability distribution function for the indirect lighting computation. Previously, you simply used a uniform probability distribution where the probability of sampling any point on the hemisphere was simply 1 over 2 pi because the hemisphere has 2 pi steradians. You can go through the full analysis. You can take the function estimator, divide by the PDF, and you end up, because the PDF is simply equal to 1 over 2 pi here, you end up with the 2 pi factor in the numerator. Now we consider a cosine probability distribution function that includes the n dot omega term. You can work out the math for this, and normalization requires you to do n dot omega divided by pi. If you now consider the function divided by the probability distribution function, then you will notice that you have n dot omega here and here, and therefore you can actually cancel them. The factor of pi goes outside the summation, and what you're left with is this simpler expression that includes pi divided by n, and inside the summation it simply has the lighting and BRDF terms. This brings up a key point in importance sampling. Because you have importance sampled according to the cosine distribution, that no longer needs to be included in the estimator, and all of the variance from the cosine term is removed. In fact, it is common in importance sampling that one can analytically cancel out the cosine term as we've done here, but even if you were to just numerically compute the function over the PDF, it would cancel out. What remains is, how do you actually generate samples according to this cosine term over the upper hemisphere? We can use an inversion method. In polar coordinates, we know the density now is equal to cos theta times sine theta d theta d phi. Remember that the solid angle that we considered earlier had the sine, but now we have an additional multiplication by a cosine. If you integrate and invert, at this point you get the cosine inverse of the square root. The square root expression is new here. The recipe is much as we did for sampling the upper hemisphere uniformly. You pick two random variables, psi1 and psi2, in the range of 0 to 1. Those are simply uniform random variables generated with your random number generator. For phi, as before, you multiply by 2 pi, so you get a value in 0 to 2 pi, which is simply 2 pi psi2. For the z quantity corresponding to cosine theta, that still lies in 0 to 1. However, now you set z is equal to square root of xi1 instead of simply setting it equal to xi1. The extra square root is very important. Finally, as in uniform hemisphere sampling, you say theta is equal to the arc cosine of c, which is equal to the arc cosine of the square root of xi1. Once you've done that, the Cartesian components x, y, and z can be obtained in the standard way from spherical coordinates. Finally, you rotate according to the surface normal so that z goes to the surface normal, or you create coordinate frame exactly as you did for uniform sampling. The only difference really is this additional square root term. You will now modify the indirect lighting estimator, whereupon you will remove the cosine term there, since you're already importance sampling according to the cosine, and instead of using 2 pi, you will use pi. Those are the only changes you need to make. This will apply to indirect lighting and the weight of the term for Russian roulette. Here are the images you will produce. This is an image from uniform hemisphere sampling. And if I compare it to cosine sampling, you can see that the variance is somewhat reduced. It's perhaps not as dramatic as the importance sampling results I've showed you in earlier lectures, but there is a clear variance reduction. I'll flip between them again. Here is uniform hemisphere sampling, and here is cosine sampling.